Let's talk about the topic of water in biochemistry. One of the most important properties of water in the body is the ability that water has to transport important biomolecules throughout the body. In order for water to be effective at transporting these small molecules, it has to be able to solubilize small biological molecules. Now, what properties of water make it a good solvent for solubilizing small biological molecules? Well, recall that the molecule of water, H2O, has this oxygen atom, and the oxygen atom is electronegative. Being electronegative means it has an electron pulling power, and that is going to give it a partial negative charge. Now, that being the case, the electron cloud, is going to be pulled in the direction of oxygen. That is going to impart a partial positive charge on the hydrogen atoms. Essentially, what we're doing is we're creating a molecule with polarity, where you have partial negative charge on one end of the molecule, positive charge on the other end of the molecule. It's this atomic structure of water that gives its solubilization properties. In order to see that, let's take an example of our familiar sodium chloride crystal. So recall, sodium chloride has a valence shell of electrons. The sodium has one electron on the outer valence shell that is all by itself. It doesn't like it. The chloride ion has 7 electrons on its outer valence shell. And the optimal number of electrons in that outer shell is 8. And so the 1 plus 7 gives the 8 complementary for sodium chloride, and that's what gives the power of holding these two together. So this 1 electron of sodium is shared with chloride, and we have sharing in that electron cloud. Now, we know that when we take sodium chloride and put it into solution, by dissolving the sodium chloride in water, this is a very, very rapid response. Of course, as chemistry shows us, this is reversible. However, the free energy change is going to be much greater in the direction of dissociating the two sodium and chloride. Now, when this happens, the electron from the outer valence shell of sodium is going to be taken by chloride to give a negative charge, and losing 1 electron is going to impart a positive charge on sodium. Now, what stabilizes these two from coming back together and forming the crystal structure of sodium chloride? Because here we have a potential of a charge interaction, which is a very strong interaction. What we need to consider now is that we are in water. I'll just draw one molecule here to give you the idea. We have a partial negative charge on the oxygen, partial positive charge on the hydrogen, so this will form an interaction. Likewise, when we have the partial positive charge on the hydrogen, we will form an interaction between the hydrogen and the chloride ion. Now, these ions are completely surrounded by water. So each one of these bonds between the partial negative or partial positive charges with the full charge on the ion is going to contribute bonding energy. The bonding energy of the water with the ions is greater than the bonding energy of the sodium and chloride ionic interaction, and so that keeps the sodium and chloride apart. It is this nature of this bond between water and its substrate to form these interactions is what lends to solubility. If water can form a productive interaction between these substrates with itself, then it's deemed to be soluble in water. The counterexample of that is to take a hydrophobic molecule. Something hydrophobic, let's say that this is a benzene ring. There's no potential interaction here with water. And if water cannot interact with this, then there's no productive water bonds, and therefore there is no solubility. Now let's examine the 4 types of bonds that we will encounter in biochemistry. In order to appreciate these bonds, let's compare them to what we're familiar with are the covalent bonds. The energy of a covalent bond is approximately 400 kilojoules per mole. We know this is a very tight bond, very high energy. It takes a lot of energy to break these bonds. These types of bonds, of course, are important for structure in biochemistry, but for transient interactions, they're just too strong to overcome. So we have other types of bonds that are often more important for biochemical reactions. The first one are hydrogen bonds. Hydrogen bonds have an energy of 8 to 21 kilojoules per mole. And these are very fleeting transient interactions. So for example, one type of hydrogen bond is the bond of an alcohol group with a carbonyl. So essentially what you see here is that we have an electronegative atom, oxygen, double bonded to the carbon to form a carbonyl, and because of its electron withdrawing strengths, it is going to be a partial negative charge. Likewise, the oxygen on the alcohol group, the hydroxyl group here, is also going to be electron withdrawing, which will essentially induce a partial positive charge on the hydrogen, allowing the formation of a hydrogen bond. The next type of bond is an ionic bond. The energy of an ionic bond is approximately 40 to 90 kilojoules per mole. And again, this type of bond is due to the interaction of 2 charged groups. So for example, if we happen to have a carboxylic acid and we have a primary amine, if we happen to be at neutral pH, we'll talk about this more when we do titration studies, the carboxylic acid will be in a negative charge. It'll be deprotonated. The primary amine will be protonated, giving it a positive charge, and so these two can form an ionic interaction. The next type of bond is a hydrophobic bond. These are relatively weak bonds, but they comprise a very important entity in biochemistry because hydrophobic bonds are very productive in especially what's called protein folding. We'll get into that in our next session. So the principle of hydrophobic bonding follows the second law of thermodynamics. This is the easiest way to explain this because we're looking at the concept of entropy or randomness. So remember, the second law of thermodynamics says that the total energy in a system is of a spontaneous reaction is increasing in entropy. So when we have two hydrophobic groups, these are going to repel water, and the water will essentially form an organized structure around the hydrophobic groups. Now, if we have two hydrophobic groups, we will have essentially two organized structures of water, and this organization occurs because the water does not interact with the hydrophobic group. So increasing order of water is essentially a decrease in entropy. In order to decrease entropy, that's creating order. So it's increasing order, decreasing randomness. This requires an input of energy, so this is not favorable. Now let's take this and put these two hydrophobic groups together. Now what we've essentially done is we still have the ordered water around these two structures, because the water, again, even if they're associated, the water cannot interact with them. But what we've essentially done is displaced this area of the water and created randomness, because we've dislodged this, and now the water forms around the two. So essentially, when we put these two hydrophobic groups together, we are increasing the entropy of water. By increasing the entropy, we are decreasing the order, and this will be an exothermic process leading to a favorable situation. Now, the last bond we need to talk about are van der Waals forces. Van der Waals forces are among the weakest forces we'll be looking at. This is approximately 4 kilojoules per mole, actually 2 to 4 kilojoules per mole. And this has to do at the atomic level. So if this is our electron, our cloud in the nucleus, we have electrons around the nucleus. Now, under normal circumstances, if we calculate the position of these electrons, they should be randomly distributed. But on occasion, we will be able to induce something like this. This essentially redistribution of the electrons will create a dipole. Two poles. One pole will be slightly negative, the other pole will be slightly positive due to the loss of electrons being shifted to the other direction. Now, once this happens, the neighboring atom can also respond to this by shifting its electrons. So we have a partial negative and a partial positive charge, one being induced by the other. These van der Waals forces are very powerful because they are so numerous, and this force can describe the hydrophobic interaction between these two hydrophobic molecules. So again, in order for solubility to occur, the water needs to interact, but in the case of a hydrophobic element, the water orders itself around, but if we put the hydrophobic bonds together, we can induce them by van der Waals, anchor them, and then the water redistributes, increasing entropy. These two forces will increase what's called the hydrophobic effect. Now, the big take-home message of all of this is that these bonds are all very weak. Weak relative to the covalent bond. But the key is that there are many of these 4 weak non-covalent interactions. And this means lots of energy. And that's what gives us stability with all of these weak interactions. It's the collective additive nature of all of these bonds. Okay, so our next topic area we need to address is the definition of pH. So pH is extremely important in biochemistry, largely because of the environment that you need to maintain for proper catalytic reactions. So let's take a look at a graph of enzyme activity versus pH on a scale of, let's say, 1 to 14. So enzymes will catalyze the transformation of a substrate to a product. This product we can measure. And if we can measure this, then we can measure enzyme activity. So essentially, in this particular experiment, what we're doing is we're mixing substrate plus enzyme, and we're going to measure the product formed. Now, if we do this at varying pHs, what we find out is that enzymes will have what's called a pH optimum. For most of the enzymes in our body, our pH optimum is going to be around the 7 mark, 7 to 7.5. If we go below this, the activity, measurable activity, which is product formed, decreases because we are out of that proper pH range. If we increase the pH, more basic, we also remove enzyme activity because the enzyme is out of its native environment. So study of pH in biochemistry is very important because of this. So what is pH? How do we get pH? Well, pH is defined as the dissociation of water into proton and a hydroxide ion. So this doesn't happen very often, of course. So the rate of this formation over the rate of this formation are not equal. We know that water does not ionize very readily. But if left to equilibrium, we can measure the concentration of protons times the concentration of hydroxide ions over the concentration of water, and we can derive the equilibrium constant. Now, we know inherently, intuitively, that this reaction is not very productive. So when the equilibrium constant is measured, it's actually 1.8 times 10 to the minus 16th molar. Now the concentration of pure water in the reaction is 55.5 molar. So what this allows us to do is to calculate the concentration of protons in the solution at equilibrium. Now, if we know these two factors, the equilibrium constant and the concentration of water, the amount of protons and hydroxide ions are going to be equal, obviously, because this is a 1-to-1 ratio when these dissociate from water. And so we can assume that the hydroxide ion concentration is the same as the proton. So if we do our algebra, this comes to 1 times 10 to the minus 14th molar squared. If we take the concentration, the square root of both sides, we see that the proton concentration at equilibrium in water is 1 times 10 to the minus 7th molar. Now, to remove the exponent from the equation, we can use our basic calculation that the definition of pH is equal to the negative log of the proton concentration, and therefore pH equals 7. So this is the definition of pH. This is the definition of neutrality. So when we talk about pH, in all cases, it's all relative to the pH of water, which is pH 7 at equilibrium, and that defines neutrality. Now, typically what we're going to be talking about are acids. So let's look at a reaction, a dissociation reaction of acid in water. So HA represents the acid, H plus is the dissociated proton, and A minus is the conjugate base. Now, depending on the acid, some acids are stronger than others, we will have a greater rate of dissociation than weaker acids. We can quantify this by calculating the acid dissociation constant. And this, again, like the equilibrium constant in water, is the concentration of products over the concentration of reactants. And this gives us our acid dissociation constant. So if we have a stronger acid, we are going to have a greater Ka, because we will have greater concentration of reactants of product over reactants. So an example of this would be 1 times 10 to the minus 2nd molar. This would be a very strong acid. If we have a weaker acid, we are going to have a reduced acid dissociation constant because we have less product formed because there's less dissociation. This, we could say, would be, for example, 1 times 10 to the minus 12th molar. That would be considered a very weak acid. Now, of course, we have our exponents here, so we want to get rid of those, make our calculations easier. So as we do in water with calculating pH, we're going to identify pKa, and this is going to be the negative log of the Ka. And all this essentially does is convert the exponent into a whole number. Now, what's really important about all of these calculations is that we want to determine the pH of a solution of acid. So here we can use the equation pH equals pKa plus log of the conjugate base concentration over the concentration of acid. And this should be familiar to you. This is the Henderson-Hasselbalch equation. So with this equation, essentially what we're doing is we're using the pKa, inherent pKa of the acid, strength of the acid, and using the concentrations of acid and conjugate base within the solution we're measuring, we're able to use this information to determine the pH of the solution. So for example, if we dump in a large amount of HA, which is the acid, that would give us, let's say for example, a ratio of 0.1. The log of 0.1 equals -1. So if we take a lot of acid, put it into the solution, we are going to be below the pKa. So it would be the pKa minus 1, giving us the pH. Likewise, if we throw in a large amount of conjugate base, let's say our ratio is opposite, so now that we are at 10:1 conjugate base to acid, then we have the log of 10 is equal to +1. So now we are taking pKa of the acid, adding 1, giving us the pH. So now we are above the pKa because we are more basic. When the concentration of conjugate base equals the concentration of acid in solution, this equals 1. The log of 1 equals 0. So this defines the pH being equal to the pKa. And this will become very important when we start talking titrations of buffering chemicals and amino acids.